Good afternoon and welcome to Automation Techniques in C++ Reverse Engineering in Lagoon JKL, presented by Rolf. Just a couple of quick notes. Don't forget to stop by the business hall located in Mandalay Bay, and Black Hat Arsenal is also in the business hall on level 2. And then one final reminder to make sure that all of your phones are silenced. Thank you very much.
Hello, everybody. Thank you for coming to my talk. This is about automation techniques in C++ reverse engineering. The genesis of this research is I was doing research for an upcoming training class in C++ reverse engineering. So I was practicing statically reverse engineering some large C++ binaries. And for the first few weeks of this, I was just using the same techniques that I've been using for the past 15 years. And it was working, but it was a slow-going, tedious process. I noticed I was spending 85 to 95% of my time creating type information, that is to say, recreating structures and assigning structures in the disassembly listing, as well as setting types to Hex-Rays variables. And because this was consuming so much of my time, I decided maybe it's a good idea to try to figure out, can I automate these techniques? So we're going to be focusing on dynamically allocated structures. We're going to be deriving metadata from runtime accesses, and then collecting this data and exploiting it within IDA and Hex-Rays. There are two primary analyses that I'm going to present. One tracks accesses to structures, and the other one is a dynamic data flow analysis tracking data from allocation sites into function arguments. So pictorially, the big picture behind why did I do this research in the first place? What is this all about? This is your stereotypical nasty looking decompilation listing, all of this naked size type pointer dereferences. Frankly, I find this stuff borderline unreadable, or at least requiring more effort than necessary. So on the other hand, when I switch to the next slide, the difference here is I've created a structure and I have set the function prototype such that both arguments are that structure and it returns void. And now you can see all of those nasty casts disappear, that this looks more or less what the original source code looked like, minus names and comments. So type information is the difference between unreadable gibberish and stuff that's pleasant and easy to read, but it's tedious to create and apply all this type information to the database. So we're going to focus on automating these tasks. So we're going to be targeting each structure that is exercised through runtime behavior. We're going to want to figure out the size of each structure, the layout, which is to say where the fields are within the structure, as well as what their sizes are. Every location within the binary that accesses the structures that we're interested in. Figure out type relationships between fields of different structures, and also we'll be interested in variable and function argument types. And there's some more experimental stuff also. So once I really got in the swing of applying these techniques, I found that I was applying more type information to my database in a matter of days than I had in 6 weeks of manual reverse engineering. For one of the targets I've been looking at, these techniques helped me to recover about 200 structures and set about the types for about 6,000 variables and Hex-Rays automatically, and apply tens of thousands of structure offsets in the disassembly listing, all automated or semi-automated fashion. So without further ado, this is the first of the two analyses that I mentioned. This has to do with tracking accesses to structures. So in this regard, I was inspired by existing academic work. I remembered a paper that I had read many years ago called Howard, and there's a few other related works such as Dynstruct, for which source code is available. So I had in mind that I wanted to experiment with ideas similar to these. However, these ideas seem to have some fundamental performance overhead associated with them. So I wanted to experiment with them to see if I could eliminate that as well as make the techniques a little bit more flexible. So what follows is my journey along those lines. So on the high level, the way these tools work is they locate and hook the memory allocation functions, malloc and free, but also things like realloc. Inside of these hooks, they record metadata about every memory allocation, where it was allocated from, what's the allocated pointer, how big is it. Then they run the programs under dynamic binary instrumentation, log every access within one of these dynamically allocated memory regions, and finally, this generates a lot of data, which we then post-process to obtain information about structures. So I'll go through these steps individually. Step one is to locate the memory allocators that you're interested in. This might differ depending upon the scenario. Up on the slide here, I have your memory allocators are imported from some other library via the import table, but it might also be the case that maybe there's a custom memory allocator in the binary, which is a function. So just locate these things, number one. Number two, hook them, redirect them into our own memory allocation functions. Again, this might be as simple as overwriting a function pointer if it's an import, or it might be more along the lines of having to hook a function prolog if it's something that's contained in the binary. The hooks themselves are not that difficult. For example, looking at the hook for malloc off to the left, first thing it does is just call the original malloc to obtain whatever pointer would have been obtained by calling malloc. Then it calls this function remember, which memorizes the details for the memory allocation, which is to say what the pointer is, how big is it, and where was it allocated from. And finally, just return that back to the caller. And the free hook is even simpler, just discard the information about that allocation and return back to the caller. So this is all transparent to the application. When it comes down to it, the application really doesn't care about its memory allocator. It's pretty much just a function that it calls to obtain pointers or to destroy pointers. So inside of the malloc hook, the remember function is going to store allocation records, which is the pointer itself that was allocated, the size, and the RVA within the image that it was allocated. So this is recorded relative to the base address of the image, so we don't have issues with ASLR and aggregating the results across multiple runs. It's going to store these allocation records in some sort of data structure. So later on, we're going to have to look up addresses within these allocations. So we'll be looking up not just by the base of the allocation, but also anywhere within the allocations. So for this purpose, usually something like a binary tree is preferred. AVL trees are good here. They have strict balancing requirements, whereas red-black trees work, but their lookups are a little slower than AVL trees. I recently realized you could use something along the lines of not quite a hash table, but sort of segment the addresses the same way that the page table translation process does it. That's yet to be explored. So remember adds items into this map and forget removes them. Okay, so that's the part where we hook the memory allocator and record allocation memory metadata. Now we're going to find accesses to these allocations. So the next step in these tools is to run the programs under dynamic binary instrumentation and provide whatever inputs you need to drive execution throughout the program. You know, if you're running Adobe Reader or something, this means provide a PDF for it to open or something along these lines. And then we're going to log accesses to the allocated structures and record it. So via DBI, we are going to insert callback routines on every memory access. So the callback routine is going to be given the address that is to be accessed by the memory access. It's going to take that, look it up within the map that we keep the allocation metadata in. And if we find the address within one of the allocation records, that means we have just discovered a memory access to one of the dynamically allocated memory regions. So we're going to log that, which is to say, let's say this instruction was observed accessing that particular address ending in 28. And we look that address up in the map, and we find that we have that same address ending in 00 with the size of 80 hexadecimal having been allocated at that RBA. So now we just log the details of that access, where the allocation came from, how big the allocation was, where the instruction that accessed it was, how big the access was, where within the structure was it accessing, and was it a read or a write? So we just run the program and collect up all of this metadata. And afterwards, we have an enormous text file, which we then take and post-process to recover higher level information. So we'll have information logged through the preceding process, such as the following, the table that we see on the slide here. So the first step is to take these things and just segregate them by the allocation site. Just take everything that was allocated from the same location and aggregate all of those things together. And at this point, if we happen to know for some reason a priori that two sites allocate the same data type, that we can at this point just merge their data together. And now we can take this information and rebuild structures from it. So sort, for any given allocation, take the accesses that we observed, sort the offsets at which the accesses took place and remove duplicates, and then simply convert those into structure declarations. Choose C data types of the appropriate size, and lay them out in the sequence in which they were observed. So that seems pretty easy. A brief digression. In fact, through this process, we don't just discover a flat list of fields, but we can discover nested structures contained within other structures. So for example, if we observed the access that we see on the top of the slide here, you can see the x86 instruction has EAX plus 8, whereas the recorded access offset is 28. So the only way that's possible is if at the time that we log this data, that EAX was pointing plus 20 hexadecimal into that particular allocation site. So that means the program is passing around pointers plus 20 hexadecimal into that allocation. And what that means in brief is that there's a structure that begins at plus 20 hexadecimal. So we can use this information to recover nested structures, not just a flat list of fields. Okay, so the picture so far was a little simplified compared to real life. As it happens, there is some noise, some imperfection in the data. Some of it's from natural causes in the source code. Some of it comes from compiler optimizations. We'll talk briefly about those and what we do about them. So first of all, it's perfectly legal to cast integer data types from one size to the other. So we might be dealing with a situation where we have a structure in the source code which has a 32-bit integer, and then if some access to that structure is actually only using 16 bits worth of it, we'll see what's in the middle column, which is the use of a 16-bit register. Or, for example, we could also just cast to the low 8 bits of that structure, of that field, and so we'll see the use of an 8-bit register. And so this casting might give us multiple different size accesses to the same location in the structure, which leads to ambiguity about what field actually is supposed to be at that location. So my solution to this and most of these related issues that we'll see is I just use the access data that we generated at runtime and then choose the configuration that agrees with the largest number of observed data points. And this turns out to work very well for most of these issues. Another issue has to do with compiler optimizations. Here again, we're assuming there's a 32-bit integer contained within a structure, and here we're testing it against the 32-bit constant, 40 hexadecimal. So the natural way to implement that in assembly language would be the topmost assembly language instruction, which is treat that location as a D word and encode a D word size constant as the last 4 bytes of the instruction. But actually, it's perfectly legal to convert the instruction into a byte-sized access instead, where since the only non-zero byte within that 32-bit constant that we're adding in is the lowest one, and just take that and turn it into an 8-bit access instead. So again, this leads to ambiguity about what is the size of the field at that location. We might see multiple size accesses. Highly related but slightly different is what if on the last slide, instead of ANDing with 40 hexadecimal, we ANDed with 400 hexadecimal? So this gives rise to a similar optimization opportunity, except since the 400 hexadecimal only has a non-zero byte at +1 into the constant, we can still convert it into a byte-size access exactly as we did on the previous slide, but we have to increment the address that we're accessing by 1, which is why you see the ESI +1 in the second assembly language instruction. So now it looks like we have this field within the structure that's not really there, that just sort of, that access arose as a result of a compiler optimization. Another issue is called store aggregation. This is when you have multiple smaller writes all targeting adjacent fields that the compiler can take them and aggregate them into one larger write. In this case, we have 2 Boolean variables right next to one another in the structure, and we're assigning both of them to 0. So rather than generating 2 instructions that move 1 byte at a time, the compiler can detect that these things are right next to one another and instead write 1 word at a time to overwrite both of those fields at the same time. So whereas the previous optimizations that we saw can lead to smaller accesses at a given location, this one can actually lead to bigger accesses at a given location. Another source of imprecision is bulk copies and assignment, things like memset and memcopy. So off to the left, we see a structure with a fairly intricate configuration of fields. Within the first 8 byte, there are 2 8-bit size fields, 1 16-bit field, and then the 32-bit field. And whereas memset, if we set this structure to 0, the code that might be generated simply overwrites 64 bits at a time of zeros, oblivious to whatever the layout of the structure is, just write bulk data. So for all of the issues so far, my solution has just been to count the number of accesses we see at given sizes and offsets within the structure, and then just choose the configuration that agrees with the largest number of accesses. And this works very well. Plus it's principled. We don't have to make guesses. We just try to optimize according to the data that we see. Now there are 2 more that are a little uglier. Unions, for example, allows us to statically assign different types and different sizes to the same location within a structure. So we might have an integer and a character pointer, let's say, in a union, that means it's perfectly legal for us to see differently sized access to the same field because there are, in fact, differently sized types being stored at that location. So my solution to this one is the same as before, and it's not a good solution. It's basically to just ignore the fact that unions exist. Unions are kind of thorny, honestly. And finally, array accesses produce these offsets, non-constant offsets. Here we have this RBX times 4 within the memory access. So I have it in mind in the future. I have some ideas for what to do about this, but for now, I'm just not handling this case at all. I just punt anytime we see an access with a non-constant location, just throw it away. No, it's not a real solution, obviously. Okay, so thus far, I've largely been talking about the existing DBI-based solutions as well as some of my solutions to the issues that I saw coming from using solutions like that one. In actuality, I did not use DBI for my implementation of this idea. There are several reasons for this. First one is I am simply not an expert when it comes to DBI, and I anticipated there would be a learning curve to it, and I wanted to see if the idea would work immediately, so I kind of wanted to come up with a quick implementation. But in fact, there are some more principled and realistic reasons to look for solutions other than DBI. So although the DBI solution is comprehensive and fully automated, it also requires that you instrument every memory access that takes place throughout runtime execution. Means every time there's a memory access, we're going to insert a lookup into a map. So this is a fairly heavyweight application of DBI, and the larger the overhead, that means the harder it is to interact with the application. The harder it is to interact with the application, that means the less coverage we're able to drive, and the less coverage there is means the a smaller amount of information we're able to observe about the structure accesses. And furthermore, no matter how we might try to optimize a DBI implementation, that fundamentally the way the solution works is by instrumenting every memory access. So there are real limitations about how far we can go with optimization. So I just described the fundamental overhead from the approach itself. There's also overhead with regards to having to track every allocation site within the program. So we're inserting these map lookups all over the place, and the more allocation sites that we're tracking at any given time, the more expensive these map lookups are going to be. So I wanted to know, experiment with maybe tracking less data at any given time could lead to better performance. And finally, these DBI-based solutions are sort of just these like monolithic black box where put in program, press button, get out structure configurations. And I'm a professional reverse engineer. Maybe I can figure out better uses to which to put that data. Recovering structures is cool and all, but maybe there's more I can do with the data perhaps. So I wanted to experiment, how could I make this an interactive tool that reverse engineers could use in a friendly fashion? The ability to choose parts of the program that we're interested in, and how do I present the results to the user in a way that's most beneficial to them while they're reverse engineering. So, right, roughly those are the directions that I'm going to explore, trying to replace DBI with some other form of tracking accesses to structures, and then allow more flexibility in what we're tracking and how we're tracking it. Performance optimize everything and try to make good use of the data, be as friendly as we can, make the reverse engineers' lives easier. So, my first order of business was to figure out some way to track accesses to allocated data without using dynamic binary instrumentation. And brainstorming about this, my first idea was maybe I can use the x86 hardware read and write debug breakpoints. So for example, every time a call to malloc takes place, just set read and write breakpoints across the entire structure. So this isn't a good idea. It does not work because we simply don't have enough breakpoints. x86 only gives us 4 breakpoints, which means a total of 32 bytes of memory that we can track. And that's not even enough to cover one small size structure. That said, though, although the breakpoint idea does not work, it does have this interesting feature where it sort of is fundamentally different in how it tracks the accesses, whereas with the DBI solution, we have to insert instrumentation all over the place and dig out the memory accesses by looking them up every time in the map. With the breakpoint approach, we can just specify, here's the memory locations that we're interested in, and then the processor effectively gives us callbacks in the form of debug exceptions telling us when that memory is accessed. So I wanted a solution with that kind of feature to it, where I didn't have to instrument everything. I could just sort of specify what it was that I wanted to track. But fundamentally, x86 hardware breakpoints can't do the job for us because we simply don't have enough of them on an architectural level. So then I remembered there was a command in the kernel debugger softice, and it's also been implemented in a couple of other tools in the meantime, called breakpoint on memory range, which allowed you to set as many memory breakpoints as you wanted and of as large size as you wanted. You can implement this in either user mode or kernel mode. So IDA also implements this, as does OllyDebug. So that sounds promising. Let's review briefly how that works. Fundamentally, the implementation has to do with virtual memory and on-demand paging. So in a demand-paged environment, processes appear to have a large address space, but in reality, they only consume as much memory as there are physical pages assigned to their virtual pages. So for example, on this diagram, the virtual page number 4 does not have a corresponding physical mapping, so it doesn't have to consume a physical page for that virtual page. The page table dictates the translations between virtual and physical pages, basically specifies the high bits of the virtual page and the high bits of the corresponding physical page with some flags and also this present bit at the bottom, which we'll talk about again in a minute. As the program requests it, the operating system can allocate more memory and basically add new virtual to physical mappings on the fly. At some point, if the process starts running out of memory, then the operating system can go around and start reclaiming memory. So this makes use of the present flag at the bottom of the page table entry for that corresponding virtual to physical mapping. So the operating system just writes that copy of that physical page to disk, sets the present bit to 0 in the page table entry, and then later on, when the program goes to try to access that page, since the present bit is not set, this results in an exception being generated. The operating system kernel catches that page fault exception, realizes that the exception arises from a page having been reclaimed and written to disk, reads the page off the disk, and then sets the present flag to 1 again, and then continues execution. So all of this happens in a transparent fashion. The user mode application doesn't even realize that anything has happened. The kernel just takes care of all of that in the background. So that's the background, that this is how the BPR memory breakpoint feature works. So we're going to make use of this non-present mechanism, where for pages that we're interested in tracking, we set the present flag to false. That's going to give us exceptions when the application tries to access the pages. If we find an access to what we're interested in, we'll log it and continue execution in any case. So here's an animation of how this process plays out in real time. So let's assume that this first instruction here is going to access memory. So let's assume that we have marked this page at EBX+4 as non-present. So then when the instruction goes to execute, because the memory is non-present, that processor generates a page fault exception. Now, we have installed an exception handler, and we're able to inspect these exceptions that come in. So first we see, was this exception our fault? Which is to say, is it a page fault that arose because we set the present flag to false on some page? So if it wasn't, we just pass it off to the next exception handler in the chain. If it was, we process it. So if it was our fault, now we are in the exact same position as the DBI-based tools are, where at this very moment, now we know that this particular instruction tried to access some allocated region that we're interested in. So right here, this is how we replace DBI, is log right in the page fault handler the details of where the allocation came from, as well as what instruction accessed it. So now we need to let the process continue execution, but it's a little tricky. So we save the address of the faulting instruction. We mark the page as present. And before we continue execution, we have to have some way of making sure that we get control again. If we were to simply mark the page as non-present and then just let the application run, then we would basically have one-shot breakpoints. We want to be able to track subsequent accesses to the same allocation. So to do that, we set the x86 trap flag, which is the same mechanism that debuggers use to implement single stepping. If the trap flag is set at the end of an instruction, it causes the processor to generate a single step exception after it executes. So then we resume execution. Now we're back trying to execute the program again. The structure access succeeds this time because that memory is marked as present. But since we set the trap flag, then now the subsequent instruction faults. So back in our exception handler, we see if this is a single step exception, is it a single step exception immediately after the last instruction that we saw, i.e. is this our fault? If not, pass it off to the next handler in the chain, otherwise process it. So now we make the page non-present again so that on subsequent accesses, we'll catch them. And then just resume execution. So that there is the architecture that I came up with for replacing DBI in tracking structure accesses, where I install this exception handler, and it runs inside of each thread that is associated with the ordinary program. So each thread just catches these page faults, implements the exception logic, and stores these accesses into a ring buffer. And then I have a controller thread which just periodically pulls the ring buffers from the other threads and deduplicates the data and logs it to disk. So since the last time I gave this presentation, I had a few optimization ideas, and some members of my prior audience also had some suggestions for me. One person suggested that having to single step inside of the page fault handler is slow because this results in an extra user to kernel mode transition. So if I were to implement a little emulator to mimic the effects of the instructions, rather than simply letting it execute and having to incur this extra user kernel transition overhead, that I might get a performance boost. And he was right. It was a nice 40% performance increase. Some other people suggested that I could use guard pages instead of setting the pages as non-present. Guard pages have this advantage of number one, the operating system has optimized pathways for them because it uses guard pages internally. And number two, that when a guard page exception takes place, that the operating system automatically marks the page as present. So this eliminates another user kernel transition where we would have to call virtual protect to mark the page as present before we could single step. That was another reasonable speed up. And I did some standard optimization tricks with like forcing things to reside on different cores. My logger thread should have low priority and it should be on the bad cores and give all the good cores with high priority to the application itself. And then I implemented a second version of the x86 emulator based on JIT. So these numbers come from my laptop. That was the trail of performance. On my desktop, it's more like 15.6 million page faults per minute, million structure accesses. It's pretty good. So another major optimization idea I had to do with only tracking specific allocation sites. So heretofore, I've shown you how these DBI tools work and the basic idea behind my replacement for it, but I haven't really told you how we apply this page fault-based memory tracking. So we could either go the DBI route and just track every allocation in the program, or perhaps we could track only certain allocations. So if we're going the DBI route of just track everything in the program all in one execution, then it's pretty simple to accommodate that we just add a breakpoint based on paging in the allocation hook, and in the free hook, we just remove that breakpoint. However, if we're only tracking certain allocation sites, we end up with situations like this where, let's say we're interested in the red region in the middle, and because we're only tracking certain allocations, that the adjacent memory regions might contain other allocations that we are not tracking, that we are not interested in. But because the technique works at the granularity of pages, that means we are going to take page faults in these allocated regions regardless, despite the fact that we're not interested in them. And so more page faults means more overhead. And this situation gets even worse if, for example, that allocation that we're interested in happens to lie right across a page boundary. We might be, say, tracking 8 kilobytes of memory despite the fact we're only interested in 32 bytes or something like this. So for best performance, we only want to take page faults upon accesses that we're interested in. So my idea here was just sort of allow the user to specify the sites that they are interested in, and then redirect these things into a custom allocator. So why not? We hook the memory allocator, we can do that. I'll let the user specify a list of allocation sites that they want, and anytime we see allocations taking place from those sites, we put those things into our own private memory allocator, and that way, that memory allocator only has objects that we are interested in tracking. We don't have any additional overhead that comes from spurious page faults. So the most flexibility you can get here is just use some sort of off-the-shelf memory allocator that allows you to, variable size accesses and this tuned performance and so on. So this is easy to implement. Usually these things are thread safe and performance tuned, and they handle different size allocations. However, these things have in-band metadata, which means you're also going to be taking page faults within the allocator itself. So for optimum performance, mostly the way I apply this technique is I use a fixed size slab allocator. Basically, I select a bunch of allocation sites, and then I choose the largest size that is allocated. And then I just create a slab allocator where every allocation is that size. And then there's no in-band metadata, and allocation and free are basically free in terms of performance. And it's very easy to do range lookups and so on. So this is how you get the best performance, but you have to be judicious about how you apply it. So the way I use these techniques in the present is basically if I want to, say, track all of the allocations in a given program, I'll just take a list of all the allocation sites, I'll divide it by the number of cores I'm willing to provide to this procedure. I'll run, say, 6 copies of the program, divide the allocation sites up into 6 groups so I can parallelize the data collection, and I'll use slab allocation to make sure it's as fast as possible. So basically, the difference here is rather than instrumenting every memory reference and looking up at the time of every memory reference whether or not it refers to an allocation, instead I just divert the allocations that I want into a custom allocator and then mark the pages as non-present and catch those in an exception handler. So that is the large-scale summary of the difference between what I did and the DBI-based solutions. Is it better? Is it worse? I can't answer that question because I haven't implemented the DBI-based one. What I can say for certain is that this is a lot more flexible than the DBI-based solution. Especially with all the performance optimizations, I'm able to target specific allocation sites. And in some cases, if the structures aren't used all that frequently, I can continue using the application interactively as though it were not being instrumented. You don't notice the overhead. Again, that depends on how frequently the structure is being accessed. So I think in the interest of time, I'm going to skip ahead to the next one and then hopefully give a demonstration of both. So as I mentioned, there are 2 different analyses that are taking place here. We were just talking about tracking accesses to structures via DBI or via non-present pages. We're not doing that anymore. This is analysis number 2. It is something completely separate. The big picture here is I want to track allocations from their allocation sites into function arguments. So basically, anytime a pointer is allocated, I want to find out anytime subsequently a function is called where one of its arguments is derived from that pointer. So for example, we have this allocation taking place at location 567. It's an allocation of size 138, and it's flowing into sub 345. The third argument and the offset is 16. So I want to record data such as function was 345, argument was 3, allocation site was 567, size was 138, and the offset was 16. So I chose to go x64 specific on this for simplicity on my part. The x64 exception metadata gives you the addresses of all of the functions within the binary. This is a change from the 32-bit Windows environment. So it tells you where the function begins as well as where's its first region, like its first try block, or it's the end of it if there is none. So then I just filter out functions that I'm interested in. Basically, I want to see, is there something that would prevent me from hooking this function? Like, is there control flow somewhere in the first several instructions? Or is there cross-references coming from somewhere else? Or things like this. So I just iterate through the instructions. I have a couple of checks that I do. And then once I get 5 bytes into the function, if none of the checks has failed, that means I have at least 5 bytes of space to work with. So I noticed in practice that Hex-Rays would generate calling conventions that did not match up with real life, whereas on x64 Windows, there is only one calling convention, fast call by default, that Hex-Rays would nevertheless generate user-defined calling conventions. So this sort of wreaks havoc on our ability to give a consistent name to an argument or its location. So I wrote a little script that just converts all of these user call function prototypes into standard fast call. And then for every function, I just make a list of all of the pointer-sized arguments as well as their argument numbers now that we have consistently numbered them according to fast call. So this is the data that I collect. I just where the function is, how many bytes in the prologue are we going to, will we be overwriting, and then how many arguments are we tracking and where are the arguments. So now at runtime, we hook the memory allocators same as before, not the paging stuff, but just keeping track of where the allocations are, where the pointers are, how big they are, and where they came from. Now, for every function that we collected metadata about, just going to hook every function in the binary, copy the leading instructions into some other memory that we've allocated, insert a jump back after those copied instructions. This is our re-entry thunk. This is if we want to actually call this function in a non-hooked fashion, this will do it. Then we record this information in the hash table, basically where is the new function entry for every function. Divert every function into a common logging routine. Common logging routine basically is a little assembly language thunk that just saves the registers and flags, calls another common logging routine, then afterwards it adjusts the return address to go back to the non-hooked version of the function, restores the registers and the flags, and continues. So then this is the C version of the logging function, which is just look up in the hash table the list of pointer-sized arguments as well as the re-entry location. And then for each argument, log it, which is to say, for each pointer-sized argument, look up, is this within our allocation map? Does this argument correspond to something that is currently allocated? And then log, if so, log the function, which argument, where the allocation came from, how big the allocation was, and the offset into the allocation. So we generate a lot of data in this fashion, 60,000 entries for my target. But that's a good thing because this data is extremely valuable. So this is a little unfortunate. I have about 3.5 minutes left. And I wanted to show you demos of all of this stuff in action. But it's looking like I'm not going to have time. That's very unfortunate. So instead, I'm just going to talk about some of the challenges that arise in trying to use this data properly, and then I'll conclude, and if I have time left, we'll take questions. Otherwise, afterwards, I'll be in the wrap room across the hall taking questions. So this is a dynamic analysis, which means it can only record information about the program which was observed at runtime through execution. So if there are locations in the program that were never accessed, but they would have had structure accesses in them, that means we aren't going to observe them. So I don't have any contributions here. Every dynamic analysis has this problem, although I did incorporate a static analysis that uses Hex-Rays to find other accesses to the same structure variables that were not observed at runtime. And a fundamental issue really is that once I've recovered my structures and I go to apply this type information in the database, basically I need to assign one unique type at every location in the database. So that presents ambiguities when I have multiple, one instruction is observed accessing multiple allocations. So for example, if I've observed this instruction is accessing these 4 allocations, I need to assign one type here, and what is the type? So as it turns out, I have the source code for this one, so I know 2 of those allocation sites allocate the same type, and as for the third one, well, there's 3 copies of that type within the other ones. So there, in fact, there is a type that we can associate with that location, but it's not trivial to know what the type is. Oops. So none of these techniques are crazy sophisticated. I've run into some serious mathematics in trying to recover every single structure in the program at the same time. Recovering one structure individually or a couple of structures, this is no problem, but if you want to recover every structure in the binary, it's not just a problem of recovering each individual structure in isolation from one another, that you have to take into account overlapping accesses and so on. This is kind of difficult. But that being said, these techniques, even if they haven't produced full automation yet, in a semi-automated fashion, they're very useful in allowing me to reverse engineer programs with structures in them in a much more rapid fashion. Like I said, I applied more type information to my database in 2 days than I had in 6 weeks of manual reverse engineering. It turned out this stuff was a better use of my time than actually reading code, which is kind of trippy to think about. So I'm still working on getting the code ready for release. I spent my time coming up with new features, but it's coming soon. So my light just went red. I am over my time, which means I'll have to divert any questions to the wrap room across the hall. Thanks everybody for coming. Sorry I didn't have time for the demos.